Morning.
Good morning.
Wanting to see, we don't have a lot of students here right now, so I'm wanting to see if we have a few more show up here in a minute or so. All right. First, are there any questions or concerns?
I have a question.
Go.
So the book that we're using online, I went through your thing and it says I only have a 2-week free.
You should, Abigail, let's see here. You should have access to it. Can you share your screen with me?
Yeah, give me 1 second.
Oh, I'm sorry, give me one moment here.
Okay.
I made it hard for you to do it. Give me one moment.
Okay.
Stop sharing. Okay, you should be able to do it now.
Okay.
Maybe. See if you can do it.
All right.
So down at the very bottom, it says share screen. You see where it says that? Abigail, do you see where that is?
I hit the wrong button and okay.
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 Okay, I see it now. So go right now. Go to the McGraw-Hill Connect.
Okay. And it says that it's expired because it only gave me 2 weeks.
Okay. Did you the other students in the class, did you have to go to the bookstore and buy an access code? Or did it come with your, or did you, how did it tell you to do this?
I was just able to click on it, sign into McGraw-Hill, and it just gave me access.
Okay, Abigail, click that renew license. Do you like Abby or do you like Abigail?
Abby's fine.
Okay, Abby, click that renew license.
Okay.
Is it letting you click on it?
I clicked on it, but
all right, let's do something else. Go back to the D2L Brightspace. Go down to click on week 13, 913. Let's see what happens. Okay, go to the first set. Go back to week 9-6 instead. I'm sorry.
you're okay.
Now click on one of those external learning tools. Yeah, that's a good one to click on. Click launch.
Oh, look, this one came up now.
Okay, so go ahead, click confirm. Go down there and just click confirm. You're in.
Okay, so
You're good. You're good for the next 17 months.
okay. Yeah, I don't know, because when I clicked on your whole link and everything, and it told me I only had a 2-week thing.
There has been a major glitch, and this was a class that I kind of took on at the last moment. But with my other classes, I had it set up so that you would pay for it with your tuition, the book.
Mhm.
And that hasn't always worked very well. And that's why I was a little worried. And I didn't know, because this was a class that I kind of took on just a couple days before before the semester started.
Oh, okay.
And so I didn't know how it was going to work, but I'm glad it's working. So
Yeah.
you got what you need right there.
Yep.
Okay, awesome. That makes me happy, because there's been some major headaches involved with getting people access to books.
Yeah.
Other issues, other questions?
Mm-mm.
Okay. That makes me really happy, actually, but I won't say anything. If you look, we will probably not finish chapter 2 today. And if you look at the syllabus schedule, that will put us a little behind. I'm trying to figure out how to make up for it, but I also don't want to speed through this chapter, because I think it's one of the harder chapters. I think in the process of this whole semester, this is probably the most difficult chapter, I think. And so I don't know how I'm going to make up for it. I'm really spending a lot of time thinking about it right now. But for right now, let's just move forward, and we'll continue. We'll just move forward, and I will extend deadlines. But let's just keep going for right now. If I remember right, we were past here, and feel free to correct me. Were we about right here?
We were by like the electronegativity,
Okay.
according to my notes.
How far were we? Were we right here? Here's the electronegativity. Sorry. Here's the polar bonds, ionic bonds. Here's water and its polarity. Were we about right there?
I think so.
Okay, let's start right there, and I will be better about remembering where we're at from week to week. But so in water, because oxygen is highly electronegative and hydrogen is not highly electronegative, the result is that the shared electrons the oxygen shares with hydrogen are pulled more towards the oxygen than they are to the hydrogen. And the result is that oxygen has a partial and negative charge on it, and hydrogen has a partial positive charge on it. And if you think about hydrogen, if you remember what that atom looks like, and I'm sorry, my nose is itching. if you think about what that atom looks like, do you remember what it looks like? What does that atom look like? How many electrons does it have? How many protons does it have?
It has one electron, hydrogen.
Yep. And how many protons? It usually equals
One.
So it has one proton and one electron. Therefore, when oxygen is electronegative and it's pulling on the hydrogens that it shares with hydrogen, the result is that we have an exposed proton here on both sides that spends more time being exposed than having an electron with it to balance out its charge. So the result is that these always have a partial positive charge to them. And almost any time that, well, let's say anytime that hydrogen is attached to an electronegative atom, it's going to have a partial positive charge on it. That's important.
Yeah, I was gonna say, can you say that again? Anytime hydrogen.
Anytime the hydrogen is bound to an electronegative atom, it is going to have a partial positive charge on it. And the reason for that is because the electron and the one electron that hydrogen has spends more time with the oxygen atom, leaving its proton exposed, which is positively charged. So with the example of water, which is H2O, the oxygen has a partial negative charge, the hydrogen has a partial positive charge. And like we talked about before, that's an electronegative element. It's an electronegative atom. Or excuse me, let me say it another way. This is an electronegative molecule.
So H2O is an electronegative molecule.
I am messing things up here. It's a polar molecule. If you think about something that has a partial positive charge, partial positive pole, and a partial negative pole, it's a polar molecule. Okay, anytime that you see hydrogen attached to an electronegative atom, like oxygen, it results in a polar molecule. And water is very polar for this same reason. With that in mind, the generalized depth of nonpolar molecule and polar molecules. Nonpolar molecules involve covalent bonds where the electrons are equally shared. Polar molecules involve covalent bonds where the electrons are not equally shared. So if you think of something as being bipolar or having a dipole, there's two opposite charges to the molecule. There's two partial charges, one on one side and one on the other. So polar molecules have this partial separation of charge, two poles being created, this dipole. And sorry, bear with me, just get a lot of pop-ups with this. I'm going to do this. Polar molecules, because one end has a partial positive charge, one has a partial negative charge, they orient themselves so that the partial negative charges can be attracted to the partial positive charges. If you think about a magnet, it has two poles to it. One of the ends repels, one of them attracts. Based on their attraction, they orient themselves. So the partial negative and the partial positive charges are attracted to one another. Always think opposite charges attract, and they're always going to orient themselves in such a fashion. So sodium, for example, here, sodium with its positive, this is an ion. So it is a cation, meaning it has a positive charge. And the water, because of its electronegative, oxygen has a partial negative charge. Hydrogen has a partial positive charge. It orients itself when a sodium ion such as, or a sodium salt, such as sodium chloride, gets dissolved in water. The ions dissociate, and the water orients itself around the positively charged ion so that the partial negative charges of the oxygen are all attracted to the positive charge on the sodium. And the partial positive charges of the hydrogens are oriented further away from the ion. This polarity, this attraction in opposite charges and separation charge, plays essential roles in chemical reactions within body cells. With regards to water and other molecules with hydrogen attached to an electronegative atom, we can work, hydrogen bonding is capable of happening. So hydrogen bonds form when a hydrogen atom that's already linked to an electronegative atom, such as oxygen, nitrogen, phosphate, when that hydrogen is linked to this electronegative atom, it's attracted to another electronegative atom so that a bridge is formed or a bond is formed. The hydrogens are important as these hydrogen bonds are important intermolecular bonds, which bind different parts of a large molecule into a 3D specific shape. The characteristics and functions of a hydrogen bonds, they serve as links between molecules. They help determine the 3D shape of large molecules. So anytime, and if you want to put up here electronegative atom, anytime here, when hydrogens are bound to bear with me, bound to nitrogen. I think sulfur is also there. So nitrogen, sulfur, oxygen, and phosphate. Anytime that a hydrogen is bound to those atoms, it can be attracted to another electronegative atom like oxygen, nitrogen, phosphate, sulfur, so that a bond is formed. These hydrogen bonds are critical when it comes to maintaining 3D shapes of large molecules, such as the DNA helix. Any questions so far?
How long did it take you to learn all this?
You know what, I learned it a long time ago because I have an undergrad in chemistry. But I can tell you that learning to explain it and learning how to say it in the most simple fashion possible is an ongoing process for me. But I learned it a long time ago. Now it's to a point of where how well can I explain it? But this is, if you want to understand how critical this is what holds the DNA double helix together. These bonds right here, holding the DNA double helix together. And I can tell you that your questions and your feedback to me helps me improve on how will I explain things, because I think a lot about it afterwards and think, okay, how could I say this a little better? So oxygen is electronegative, hydrogen is electropositive, which means it tends to take more of a partial positive charge. This means that each, what did I do? That wasn't what I meant to do. Give me 1 second. It means that each okay, so let me back up. Oxygen is electronegative, hydrogen is electropositive. This means what?
Oxygen. The electrons are pulled.
Pulled by what?
The
Are they pulled more by the hydrogen or are they
Yes.
pulled more by the oxygen?
The electrons are pulled.
Oxygen.
Yeah, they're pulled towards the oxygen.
Yep, they're pulled towards the oxygen. So what is the result with regards to hydrogen? Does it become, go ahead.
More negative.
You know what? And this is not a really greatly worded question. Oxygen pulls electrons away from the hydrogen. And the result is that you have the hydrogen on, the proton on hydrogen is more exposed. Does that make sense? And if the proton is more exposed, because the proton is positive, the hydrogen is going to become more positive.
Yeah, I have it in my notes. I just didn't.
And I think this is, if this question, I would never give you this question on an exam, because the one you need to know right here, are we referring to the oxygen becoming more negative, or are we referring to hydrogen becoming more negative? Or are we, in this same idea here, are we referring to the oxygen becoming more positive or the hydrogen becoming more positive? And so I would never give you this one on an exam unless it's worded a little better than it is right there. So one more type of bond to talk about, Van der Waals forces. If you remember at the very beginning of this chapter, we talked about atoms we draw them out so that they have electron shells and the electrons orbit in those shells. However, even though we draw it out that way, because we have to be able to draw them somehow, even though we draw them that way, we know that the electrons orbit in a cloud. They orbit in a cloud more than orbiting in single rings. And so because they're so small and they're moving around moving around the nucleus, they're so small that at any point we can't pinpoint exactly where it is. They're moving really fast and they're really small. So the result is that rather than having rings or specific orbits around the electron, we have a cloud of electrons where the electron at any given moment can be somewhere within that cloud. And these clouds can show random fluctuations in densities. So at any given moment, one side of the atom may be more positive than the other side. So at any given moment, one side of the atom may be more positive and the other side may be more negative. So this is similar, if you think about this, rather than thinking about a polar molecule when we have covalent bonds being shared, or we have covalent bonds and electrons being shared. Think of this as a polar atom, where at any given moment, one side can have more of a positive charge and the other side a more negative charge. With that in mind, the same thing occurs. You get a charged dipole, where one side is more positive, one side is more negative, and it's attracted to the opposite charge on another atom that's got one side more positive and one side more negative. These forces are important to protein folding and the bonding of proteins to each other, and the interactions of lipids within the cell membranes. Any questions about this? So let me repeat one more time. Think of this as being, rather than a polar molecule in which atoms are being bound by covalent bonds, think of this as a polar atom, where you have a partial positive charge and a partial negative charge across the atom. And then opposite partial charges are attracted to one another. These forces are important to protein folding and the bonding of proteins to each other, and interactions of of lipid molecules within the cell membranes, which we'll talk about more next week. This is just a summary talking about the different types of bonds we can produce. So we can produce ionic bonds, we can produce covalent bonds, where we have single covalent bonds where there's just one pair of electrons being shared. We have double covalent bonds where there's two pairs of electrons being shared. We have nonpolar covalent bonds where the electrons are being shared equally. We have polar covalent bonds where we have an electronegative atom that's pulling the electrons more its direction. We have hydrogen bonds where the electronegative atom is bound to a hydrogen, which leaves the hydrogen with a partial positive charge that can easily be attracted to a more electronegative atom on another molecule. And van der Waals, where there's a partial charge difference across the molecule or the atom. Sorry, partial charge difference across the atom. Okay, coming back up. Hydrogen bonds are similar to ionic bonds because of what? What makes them similar?
Is it the opposite of charge attractions?
Why do you say that?
Because I feel like the hydrogen is pulling, like you said, it acts more like a magnet.
And the ionic bonds are doing the same thing.
Yeah.
You're right. Good job.
Woohoo!
Okay. Which ones are stronger? The hydrogen bonds or the ionic bonds?
Hydrogen.
Well, let me talk about it a different way. What if what happens to make an ionic bond?
You're transferring electrons.
If you're transferring. And so one atom has a complete opposite charge, complete positive charge. One has a complete negative charge. In hydrogen bonds, it's just partial positive and partial negative charges.
Okay.
So which one is stronger?
Ionic.
You're right. Which one is the strongest out of all the, before we do this, what are the 4 different types of bonds?
Ionic.
Ionic,
Covalent.
covalent, somebody else. Ionic, covalent,
hydrogen bond and the van der Waals force.
van der Waals. Okay, which ones are the strongest? out of those four?
Ionic,
Hmm.
one of them.
It's kind of strong, but there's another one that's stronger.
Covalent.
It's a covalent because the electrons are being shared. What is the weakest?
Hydrogen.
It's close, but there's another one that's even weaker because it's random fluctuations in the electron cloud around an atom.
The Vander.
It's the van der Waals. So it's covalent because they're being shared. It's ionic because the electrons are being transferred completely to another atom, and then they're being held together by complete opposite charges. Complete positive charge, complete negative charge come together in an attraction. Hydrogens are a partial positive and a partial negative charge. Van der Waals are random electron cloud fluctuations that are resulting in random partial charges across the atom that are, and then attract partial opposite charges attract within the atoms. So shared first, ionic next, shared covalent first, ionic next, hydrogen bonds next because it's only partial positive and partial negative charges. And van der Waals is last because it's random fluctuations in the electron cloud around a given atom. So water, talked about how this is a really polar molecule, makes up 60 to 80% of most living cells. It hydrogen bonds with itself and with other molecules. Depending on how the molecules interact with water, they are being described as three ways. The first one is hydrophilic. What does hydro mean?
Water.
Water. What does philic mean? Philic means like
It's
water,
palatable.
love. It means loving. So loving, as my mother makes fun of me. It means loving. So hydrophilic means water loving. You want to be with it all the time. Hydrophobic, if you think about a germaphobe, what does that say?
They don't like it.
Yeah, they don't like it. You're just like, ew, 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 ew. Don't get near me. Don't touch me. So these are things that don't like water. Well, like attracts like. So things that are hydrophilic like polar water because they're also polar. Because water is polar, things that are non-polar are hydrophobic.
Can you give us?
Go ahead.
Can you give us an example of the hydrophobic? Just I just need a visual.
Like an oil.
Oil and water. Okay. Okay. Thanks.
Yeah. Amphiphilic or amphipathic is where one part of the molecule is hydrophilic and another part of the molecule is hydrophobic. Like in this case, a fatty acid or excuse me, a phospholipid. This is the plasma membrane on a cell. Has two layers the phosphates automatically direct themselves out towards the water because they're ions, they're very polar. And the fatty acid tails, the fat tails, stay in the center. And so they're more secluded from the water. If you think anytime that you poured, if you look at the street right after it starts to rain, and initially there's oil all over on the road. And within a few minutes, depending on how fast it rains and how hard it rains, within a few minutes, the oil pools to certain spots. Initially, it's all over the road. And within a matter of minutes to sometimes seconds, it starts pooling to certain areas. And it does that to minimize how much contact the oil has with the water.
So the oil is the amphrophilic.
It's the oil is hydrophobic.
Okay, that's what I have. Okay.
And so it moves itself, it interacts with the water in such a way that the goal is to minimize how much contact there is with the water. So the next time you look at oil in your sink or oil in a thing of water, that's what it's doing. It's hydrophobic, so it's minimizing, it's moving in such a way that it minimizes how much interactions it has with the water. So all the oil in the center of that pool doesn't have any interaction with the water.
So what would be an example of the
Amphiphilic would be like a phospholipid, where the head is polar, it's very charged. And the fatty acid here is very non-polar or hydrophobic.
Okay.
And we'll talk more about that in the next week or so. So water, because it can hydrogen bond with itself, it can hydrogen bond with other things, and polar things attract one another. So polar to polar attractions with compounds. Water has certain vital chemical properties. The first one is it has a high heat capacity. The thermal stability of water helps to stabilize the internal temp of the water. Now, how does it get this high heat capacity? What high heat capacity means is that it takes a lot of heat to raise the temperature of 1 gram of water 1 degree Celsius. Why does it take that much heat? It takes a lot of heat to get water to change from a solid to a liquid. It takes a lot of heat to get water to change from a liquid to a gas. Why does it take so much heat to change the temperature of it? What do we know about water so far?
Is it because it's a polar molecule?
It's a polar molecule, so easily partial positive, partial negative charges attract. What else does it do?
Evaporate
How does it evaporate?
through heat energy.
And let me ask you another question. Let me back up. So it's a polar molecule and it's got an oxygen attached to two hydrogens. What is it? It's polar, but what is it also capable of doing? Changing, but how does it change? Someone help her. I know we have a lot of people here. Someone help her.
Is it the liquid to the gaseous state?
Yeah, the other thing that it does, so it's polar, it's got partial positive, partial negative charges that attract one another. It also can hydrogen bond with itself. And you have to break bonds to generate heat. Bear with me just for a moment here. I'll stop sharing just for a moment. So I have this bottle of white water right here. Why does it stay together? Why does it stay together as a liquid? Why doesn't it just immediately evaporate? I mean, I can take off the lid and I'm going to be careful of my laptop here. Why doesn't it just evaporate?
Well, there's no heat source.
Well, there's heat in the room. How much heat does it need? Why does it need a lot of heat? I mean, let me give you another example. Dry ice. If you've ever seen dry ice, do you ever see dry ice? How does it behave? It's in a really cold freezer, and what happens the second you expose it to room temp?
It starts to break down.
Well, it starts to break down, but how does it break down?
I don't know.
It kind of looks like fog.
So it looks like a gas, right?
Yeah.
Kind of looks like a gas. Does that make sense? Is that clear? Dry ice is carbon dioxide. It's frozen carbon dioxide. It's somewhat electropolar, but one thing that it doesn't do that water does do is, if you think carbon dioxide is one carbon and two oxygens, what's one kind of bond that you can see with H2O that you don't see with carbon dioxide when it comes to them interacting with one another molecules wise?
Hydrogen bonds.
Yeah, water will hydrogen bond, carbon dioxide does not. There's no hydrogen in it to do it. So the high heat capacity is because of how much heat it takes to change the bonds, hydrogen bonds of the water. And then give them some more energy to start circulating. And random breaking of bonds and rebinding of bonds. So the high heat capacity is because of the polarity, the partial positive, partial negative charges attracting, in addition to the hydrogen bonds.
Okay.
The calorie, if you think about calories like on your food, the ingredients label, a calorie is the amount of heat required to raise the temperature of 1 gram of water 1 degree Celsius. When we think of our food, the food that it says calories, it's actually measuring it in kilocalories. So when you look at your calories on your food labels, it's kilocalories. So that's the amount of heat required to raise 1 kilogram, which is 1,000 grams of that 1 degree Celsius. An additional property of water is its high heat of vaporization. Water has a high heat of vaporization. It takes a lot of energy to change the water from a liquid to a gas state. Why is that the case? What's going on in the water? When you see steam coming off of a pot, what you're seeing is individual water molecules breaking loose from the pot of water, and entering into the atmosphere. The high heat is because you have to be able to break the hydrogen bonds to release each water molecule. So when I stop sharing just for one moment here, when we look at a bottle of water, rather than just thinking of it as a liquid, let's think of it as a bunch of H2O molecules, each of those little oxygens attached to 2 hydrogens interacting with one another and hydrogen bonding, and that's what keeps them all in the liquid. You may randomly break, as I move the water, you may randomly break the bonds, but they immediately reform with other molecules. If I add enough heat to this, I can start releasing water molecules from the overall bottle. That's the heat of vaporization, or the heat of evaporation. Evaporation has a cooling effect on the environment because it takes the heat, it sucks up the heat. So for example, sweating cools the body because you secrete water on your skin. You start working out, your body temp is going up, you're getting hot, and the water is secreted onto the surface of your skin. The heat of your body causes that water to vaporize and turn into a gas. And it removes the heat from the body in the process. Also, if you remember, we talked about how water is really, really polar. And polar things like polar. So we have hydrophilic substances that dissolve really easily in water. And there are many, many polar compounds. Therefore, water is a universal solvent in that it easily dissolves and hydrates other polar molecules. When we dissolve sodium chloride into water, the sodium and the chloride start to, they break up, and then the water orients itself in such a way that the partial negative charges are attracted to the negative charge. Excuse me, the partial positive charges on the hydrogens are attracted to the negative charge on the chloride ion. And in the case of the sodium, the partial negative charges on the oxygen are attracted to this positive sodium ion. Forming what are called biological colloids, where these are they're isolated from one another based on the opposite charges attractions. Initially, remember, sodium and chloride make an ionic bond. We put it into water, and the water disassociates the ions, breaks up the ionic bond and separates them. A solution is defined as a uniform mixture of two or more substances. The solvent is the dissolving agent, like water, and the solute is the substance that's being dissolved. Water is very reactive. I'm gonna pull up the whiteboard just for a second here. And define some terms. Hydrolysis reactions remove water. No, wait, I'm sorry, they add water. Mom, it's really warm in here. Can you? Thank you. They add water. And I'm going to say H2O. They add water. Dehydration reactions, if you think about dehydrating things. Dehydration reactions. Remove water. monomers, if we think about, if you've ever played with blocks or Legos, monomers are individual blocks or subunits, individual subunits. If you think mono is one, so individual subunits. Come on. Of course it didn't. Okay. So monomers, it won't let me finish typing that in there. So monomers, individual subunits. Polymers are monomers attached to one another. So individual subunits being bound to one another. Bound. A polymer is defined as one, let's see here, two or more subunits bound to each other. With that in mind, dehydration reactions are used. So we remove a water to bind two monomers into a polymer. Remove a water. A hydrolysis reaction is used to break up a polymer into individual monomers. So we introduce a water to break up the monomers of a polymer. Thank you. Also, Mom, that's here. Adhesion is when water, pick her up. Mom, can you pick her up? Give me, I'm sorry, we just had someone come to our house. Mom, can you pick her up, please? Okay, all right. I apologize.
It's okay.
So adhesion is when the partial charges of water are attracted to the charged surfaces of are attracted to charged surfaces. For example, glass has a positive charge. The partial negative charges of the oxygens on water molecules are attracted to the glass surface. Water also is cohesive in that it hydrogen bonds with itself to form, to allow for us to have liquid water. It also creates a surface tension. She's good now. One other thing that water is really good at is it's got a cushioning effect. For example, you drop a marble into a glass of water. When you first drop that marble, I don't have a marble, but I have this bottle here. You drop the marble in, and it drops fairly fast, right? It drops fairly fast. It hits the surface of the water. And what happens to the rate at which it's dropping?
Slows down.
It slows down. That's the cushioning effect. And realize that all of these properties outside of the hydrolysis dehydration reactions, all of these properties are because of water's ability to hydrogen bond and the fact that it's polar. All of these properties are because of water's ability to hydrogen bond with itself and because it's a polar molecule. Onto some more simpler definitions. A mixture is substances where two or more components are physically intermixed. There's three basic types of mixtures. There's solutions, like liquid water. There's solutions where there's homogeneous mixtures of components. There's colloids that are heterogeneous mixtures or emulsions where the solutes are larger than those in true solutions. However, they don't settle out with gravity. Nevertheless, the individual particles, if you shine a light on that colloid, the individual particles can scatter light. These same colloids can exhibit a solid gel transformation, so a reversible transformation from a fluid to a solid. An example would be Jello. Or the cytosol within a cell. Suspensions are mixtures with large, often visible solutes that will settle out. If you think about a suspension, a good example of a suspension is, I don't have any children, but I do have pets. And when the vet gives you a medicine and tells you to shake it before you give it, before you dose it out. He's doing that because the medication within the solution that they put it in can settle out. It's a solute in that case. It's a suspension. An example of a colloid, same kind of medicine that I've had to give my cats, that's in glycerol. It doesn't settle out. The medication, whatever it is, doesn't settle out with gravity. a mixture versus a compound. A mixture can have a variable composition. One major way that you can just distinguish a mixture from a compound is compounds tend to be hydrogen bound. They tend to be covalently bound. They tend to be bound to one another somehow, whether it's covalent, hydrogen, or ionic. They're bound to one another. A mixture, they're not bound to one another. So a mixture's composition, you can vary the amount of each substance in the mixture. In a compound, you cannot vary the amount of each element in the mixture, or you can't vary the amount of each element in the compound. In a mixture, the individual substances or atoms are not, or molecules are not chemically joined together. In a compound, they are chemically joined together. In a mixture, each substance in the mixture keeps its own properties. In a compound, the different components within the compound will change based on what they're bound to. Because of the chemical binding. In a mixture, each substance is easily separated. In the compound, it can only be separated into its elements using chemical reactions. Examples of mixtures are air, seawater, and most rocks. Examples of most compounds are water, carbon dioxide, magnesium oxide, and sodium chloride. Turning back to the idea of water, and you know what? Let's take 8 minutes. Let's come back at 9:50. I don't know about you guys, but I'm a little tired this morning. Let's
It's a
come
lot of
back.
information.
It is a lot of information. This chapter has a lot of information. That's why I'm trying to go reasonably slowly through it. There's a lot of information. But let's take 8 minutes.
Sounds good. Thanks.
Good.
Paisley, come on. Paisley, she's not in here. Come here, Bubbles. Come here. Oh, she's not in here. Who's here? She's not here. Come on, Paisley. Come on. Paisley, come on. Not here. Where did she go? Yeah, where did she go? She's okay. She probably needs to. Okay, this is all yours. She was looking for you too. Wendy Lear, are you here?
Yeah, I'm here.
Do you know that it's saying that you've dropped the course?
Oh, really?
Bear with me. I'm just reading an email I just got.
Okay. I'll have to just get a hold of them.
Yeah, get a hold of them, know that you're continually welcome. Yeah, but find out because it's saying a non-tuition thing.
Okay,
Is
I'll
that
get a hold
possible?
of them.
Yeah,
I'll call
Just look-
Monday.
yeah, just look into it.
All right, thanks.
You're welcome. Okay. Okay. All right, so let's come back into this. So if you remember what it means to ionize, ionizing meaning you're forming two ions. So water is capable of ionizing with itself. So we have two H2O molecules in a reaction. And one of the molecules takes the hydrogen off the other molecule. And the other molecule is left with an OH and a negative charge. The hydrogen that takes the hydrogen, the water molecule that takes the hydrogen ends up with a positive charge and an extra hydrogen. The other molecule is left with an OH and a negative charge. In pure water, their concentrations are equal. And therefore it's a neutral solution. An acid, so the result of this ionization is that we end up producing an acid and a base. An acid is defined as something that easily gives up a hydrogen ion. And a base is defined as something that easily takes up a hydrogen ion. So this is an acid. It will easily give up this hydrogen, one of these hydrogen ions again. And this base will easily accept another hydrogen ion.
So acid takes and a base gives.
Acid, opposite.
Okay, so an acid gives and a base takes.
Correct. So acids and bases they're charged and they easily dissociate in water. Acids release protons or hydrogen ions. If you think, what's a hydrogen ion? A hydrogen with a positive charge is what? A hydrogen atom that has a positive charge. How many protons does a hydrogen have?
One.
How many electrons does the regular normal atom have?
One.
One.
Yeah.
So if a hydrogen has a positive charge, what's missing? What's been given up? only way for a hydrogen ion to have a positive charge is if the electron is removed, right? Sound about right? Because we know that protons are positively charged, electrons are negatively charged, and they cancel one another out with their charges. However, if we remove the electron of hydrogen, we're left with just a proton. That's all that the atom contains. So acids release these hydrogen ions. They keep the electron, but they give up the proton. Acids are proton donors. Most common acids in the body, and maybe not so much in the body, but that we talk about. I think acetic acid is found in the body though. Hydrochloric acid is what's secreted in the stomach. Acetic acid is the acid that you find in vinegar. Your classic vinegar is about 4% or 3% acetic acid in water. Carbonic acid is the major acid found in the blood. Bases dissociate and are anions that let's say that, let me put it this way, bases are anions that easily take up protons. They're hydrogen ion acceptors. Come here, Pacers, come here, baby. The most common bases are bicarbonate and ammonia. So remember, acids easily give up hydrogen ions, bases take them up. And the most common bases in the body are bicarbonate and ammonia. You've probably heard of this scale before. This is a pH scale. The pH scale measures uses the concentration of free hydrogen ions or protons within a solution. This scale is also logarithmic. So each successive change in the pH unit represents a 10-fold change in the hydrogen ion concentration. If you look at that equation right here, this pH equals the negative, remember it's the negative log of the hydrogen ion concentration. So what this means is that as the hydrogen ion concentration goes up, the pH goes down. It's the inverse of it by a factor of 10. As the hydrogen ion concentration goes down, the concentration of hydroxide increases and vice versa.
Okay.
So sometimes for me, the easiest way to think of pH is to think that, bear with me just for a second here. Easiest way for me to think about this is I think pH equals one the pH the higher the hydrogen ion concentration, the lower the pH. And the last thing that you need to remember here is rather just, that it's the inverse. So the more the hydrogen ion concentration, the lower the pH. But know that it's changing by a factor of 10 because of that logarithmic scale. So the more acidic a substance is, the lower the pH. And the more hydrogen ions it has in that solution. So the more basic a substance is, the less hydrogen ions it has in it, and the higher the pH value.
So
Once
wait,
you-
more
go ahead.
basic the substance is, the lower the hydration concentration is, and it's a higher pH.
Okay, say it one more time.
So the more basic the substance is, the lower hydrogen concentration and a higher pH.
Correct.
Okay.
So as the hydrogen ion concentration goes down, the concentration of OH is also going to increase. So the base levels are going to go up. The scale is a scale of 0 to 14 or 1 to 14. Let's say 1 to 14, where 1 is the most acidic and 14 is the most basic. Seven is neutral. So blood is a little basic. Stomach acid is about 1 or 2. And just so you know, a soda pop is about 1 or 2 when you first open it. If you've ever had acid reflux or heartburn, the reason it hurts so bad is the acid is moving up into your esophagus. Thankfully, I cannot remember a single time I've ever had it.
I have a quick question.
Go.
So like, for instance, like the acid reflux, for instance, I've had a lot of that, just for instance, like during pregnancy. So my question just is, it's a little off topic, but like, for instance, like eating, those chewable, when you have acid like reflux, you eat those like chewable, I forget off the top of my head what they're called. What does that?
The Pepsid kind of things, or the oh, what
Tums?
are they called?
Yeah, they're like the chewy.
Alka-Seltzer?
Yes. So like, what does that do to help balance? For instance, like
It's a base, and
It's a
so it
base.
neutralizes the acid. It reduces the amount of free hydrogen ions. It's a really good question.
okay,
So
Can you
it's essentially
that part?
taking, if pH is a measure of the amount of free hydrogen ions, and the more acidic something is, the more hydrogen, excuse me, the more, no, that's right. The more acidic something is, the more free hydrogen ions it has.
More, okay.
When you
Thank
take that Alka-Seltzer, it's binding up those free hydrogen ions, bringing down the acidity.
Okay.
That's
Does
why
that-
some people drink milk.
Yeah.
Yeah.
Mhm. Actually, milk, wait, I think milk is actually kind of acidic. But it probably works similarly, but milk is actually kind of acidic.
Okay.
But if someone gets poisoned by accidentally drinking a base, they will often ask them to drink milk.
Milk. Yeah.
Yeah, I think milk actually has, it's on another diagram that I have somewhere, but it's got a pH of about 5.4 somewhere in there.
It
Is
is
that-
right here. It does say.
Oh, it does say 6.5.
Yeah, right beside
Okay.
saliva.
I thought this was the same diagram. Yeah, it's about 6.5.
Okay.
But something, even though it's still, this is much more acidic than this. And so it can partially neutralize something because it's going to bring down, if you drink this, it's going to bring down the original pH to somewhere below 2, or, if it's stomach acid, you mix something that has a pH of 6.5 with something that has a pH of 2, and you're going to get maybe a pH of 4. So somewhere a little lower here. Does that make sense?
And that would fall in the same like category as far as like orange juice and stuff as well, correct? Or is that something that's more of a higher?
Orange juice is I don't know where orange juice sits on that scale, but it's
Okay.
somewhere, it's probably about 4.
Okay.
So one other thing that I'll mention here, remember that this is a factor of 10. So a pH, going from a pH of 7 to a pH of 8 means that the hydrogen ion concentration has been reduced by a factor of 10.
So does the pH scale only go to 14?
It only goes to 14. So what that probably means that even though, and when you say 10, this is 10 to the negative 14. And if you think about that, what that actually is, are what that actually is. Bear with me just for a second. I'm trying to erase my thing. What that actually is actually, let's type it out. 0.
It's not typing.
Oh, of course it's not typing. Okay. 0.000 000 000 0 1 2 3 4 5 6 7 8 9 10 11 12 13. I think that's it. So that's the amount of free hydrogen ions by a factor of 10 when a solution has a pH of 14. So it probably still has some hydrogen ions, but a pH of 1 is this. Do you see do you see the massive difference? Each one of these decimal points is a factor of 10. Each one of these zeros. This is a pH of 1 for the free hydrogen ion concentration. This is a pH of 14. So strong and weak acids and bases. So we talked about how an acid is defined as something that gives up a hydrogen ion. And a base is something that binds it easily and takes it up. A strong acid, immediately you put a strong acid into water and immediately gives up the hydrogen ions. A weak acids don't disassociate that easily. They don't give up that hydrogen ion as easily. A strong base immediately binds up all the hydrogen ions it can. A weak base may or may not take them up. Now, I haven't shown you guys because we don't have a lab class together, but I'll show you right now. I have, if you look right, actually that's the wrong arm. Do you see on the very back of my arm that white scar that runs up and down my arm?
Yeah.
You see that it's probably about 3 or 4 inches.
Yeah.
Mm-hmm.
That was an acid burn.
Oh my.
And the way I got that was, and this is just for lab safety, when you actually are finally are allowed in a lab and you can actually take a lab class. Lab safety, I was in a lab, I was working in a hood, I was wearing goggles, I was wearing a lab coat, I was doing everything I should have been doing, except for recognizing how caustic that acid was. And it probably took it, I was putting it into bottles, I was pouring this acid into bottles, and the last bottle fell over and the acid went up the sleeve of my lab coat and burned me. And it's what they call formic acid. And you probably are not familiar with that. I was not really familiar with it. But it's the same acid that ants inject into you when they burn you, when they bite you. And so it took maybe about 30 seconds for that to happen. You know, actually it took about 3 seconds for me to recognize that I'd been burned really badly. And it took about 6 months to heal. Now, my question is, how do acids cause so much damage? It's not like they're generating heat that's destroying things. What they're doing is they're spilling out a bunch of hydrogen ions to your skin that bind to the different bases on your skin, denaturing and destroying all those proteins. That's how they burn you. And bases do it in the opposite. They usurp all the hydrogen ions and they pull them off things if they can. And that's how they burn you.
Would that also follow in the same category as far as like, by instance, getting burned by oil, like cooking oil? Or
I think that's a heat thing. I still
heat
think
thing,
that's a
okay.
heat thing.
Okay.
But so let's remember the strong acids dissociate really easily, give up hydrogen ions really easily. Weak acids don't dissociate so easily. They don't give up those hydrogen ions as easily. Strong bases quickly bind up hydrogen ions. Weak bases may or may not, depending on how they feel at the moment and whether or not they want to. Buffers are things that withstand changes to pH. And they are a combination of a weak acid and a weak base that carefully regulate the homeostasis of the acid-base pH balance. They resist, so when they're present, if you add an acid to a substance, they will, the weak base in that buffer will immediately bind up the free hydrogen ions to minimize the pH change. And if you add a base to a substance, the buffer will work to bind up the hydrogen ions. The weak acid will release the hydrogen ions to minimize a major change in pH. I think, so you saw that the pH in blood was about 7.4. And we're constantly having changes in our pH. And the buffer in our blood, which I think is on the next slide, the buffer in our blood, yes, is a combination of this weak acid and this weak base. When there is a rise in, when the pH drops, this acid gives up hydrogen ions to bring the pH back to where it should be. When the pH increases, this base will bind up the hydrogen ions to bring it back to where it should be. So this reaction can go either way. Depending on the pH of the solution. This weak acid can either give up hydrogen ions and bring the pH back down, or the base can take up hydrogen ions and bring the pH back up. apologize. I'll touchy computer. A substance that is very acidic may have a pH of 1 or 2. This means that the acidic substance has a what?
A high concentration of hydrogen ions.
Correct. Correct. What would it, let's say, so let's change this for a second. The substance is very basic and may have a pH of 1 or 2. Or excuse me. The substance is very basic and may have a pH of 10 or 11. This means that the basic substance has what?
A low concentration.
A low concentration of hydrogen ions. It may also have a high concentration of these hydroxide ions. A buffer, I can't believe I keep doing that. Very touchy little mouse pad. A buffer will release hydrogen ions if the pH does what?
Rises.
Wait, think about it again.
Falls.
If the pH falls. Actually, no, if it rises, you're right, if it rises.
I was like, it's in my notes. Did I write it down?
I apologize. You can tell I can get myself confused here, and I apologize. So a buffer releases hydrogen ions if the pH rises because it becomes more basic. A substance that dissociates into 1 or more hydrogen ions and 1 or more anions. Remember, a hydrogen ion, an ion with a positive charge is a cation. So a substance that has an anion has a negative charge. So a substance that dissociates into 1 or more hydrogen ions and 1 or more anions is a what? Guys, what gives up hydrogen ions?
An acid, a strong acid.
An acid. Any acid. It's, you know, weak acids still give them up. They just don't do it as quickly. A substance that dissociates into cations, meaning possibly a hydrogen ion, and anions, a base. Oh, you know what? Let's not do this. That's not the right answer. A substance that dissociates into cations and anions, neither of which is a hydrogen ion or a hydroxide ion, is what?
Neutral.
Not exactly. What compound do you know of? What type of compound do you know of that would dissociate in water into cations and anions? This is a shift of gears.
Ionization.
Or an ionic compound.
Okay.
Okay, it's an ionic compound. A proton acceptor is what?
A base.
A base, you're right. A measure of the hydrogen ion concentration is what?
pH.
Correct. A proton donor is what?
Acid.
It's an acid. A chemical compound, I have a very, very touchy little mouse pad here. A chemical compound that maintains pH by converting strong acids or bases into weaker ones is what?
Buffer.
It's a buffer. Good job. I think the rest of this chapter gets a little easier conceptually. I think we're past the more difficult parts. Hopefully, I really hope so. I'm trying to remember. Talking about energy, potential energy versus kinetic energy. Energy is defined as the capacity to do work. Energy exists in two forms. So this is work capacities, the ability to do work. With each of the two forms of energy being able to be transformed into the other. Potential energy is stored energy. It's inactive energy that has the ability to do work, but isn't doing it at that moment. Kind of like the food in your fridge. It's a potential energy source, but at that moment, it's not doing it. A kinetic energy is energy in action, performing work by moving objects. So this is kinetic energy is when you've eaten the food and you're breaking it down and using the energy from it to do other work within your body. So potential energy is stored energy. Kinetic energy is energy in motion. Different forms of energy. We have chemical energy. This chemical energy is energy stored in the form of chemical bonds. So ionic bonds, covalent bonds, hydrogen bonds. We break a bond, we release energy. We make a bond, we store energy. Electrical energy, the movement of charged particles. So this is a current. When charged or a movement of charged particles across our ions across a membrane. Specifically how neurotransmission works. We will talk a lot about electrical currents in a few weeks here, because that is the way all of our cells that's how probably 50% to 80% of the physiological processes work. Mechanical energy, energy that's directly involved in moving matter. Radiant energy, the energy that travels in waves that vary in length. So this would include X-rays, ultraviolet rays, photons from the sun, and so forth. When you talk about another example, electron wavelengths, when you probably in lab you talked about electron transmission microscopes or transmission electron microscopes. and scanning electron microscopes. They're using these energy waves that of electrons. Mechanical energy and muscle contraction. Extending the arm by contracting the bicep. Excuse me, extending the arm by contracting the tricep. Contracting the arm by bicep flexes the elbow. Chemical reactions occur whenever chemical bonds are formed. Remember, if a chemical bond is a form of potential energy. So chemical bonds occur whenever chemical bonds are formed, rearranged, or broken. Chemical reactions can be written as equations. If you remember that buffer equation, that carbonic acid, the two arrows, bicarbonate ion and hydrogen ions. The reactants are the substances reacting in the chemical reaction, and they're on the left side of the reaction, like right here. The products are the substances produced at the end of the chemical reaction, like methane right here. So we mix we combine 4 hydrogen with 1 carbon, and we make methane. These are the reactants. These are the products. This is a product. And this is a chemical equation. Reversible reactions can go both from left to right or from right to left, depending on the circumstances. These arrows should be over in here. So a reversible reaction is symbolized by a double-headed arrow. The law of mass action says that the direction of a reaction is determined by the relative abundance of the products and the reactants. The more abundant the reactants, the more the reaction will move forward. The more abundant the products, the more the reaction will go backwards. So the more abundant substance will be the one that's reacting. When we reach equilibrium, the ratio of products to reactants is stable. They're both reacting and breaking. They're both reacting, both the products and the reactants on both sides of the equation are changing in equal amounts. This type of reaction we'll talk about at length in future chapters. So all reactions are theoretically reversible. Bonds can be made, they can be broken, they can be remade. If a forward reaction dominates, the product will accumulate. If the reverse reaction dominates, this side of these substances will accumulate. When neither the forward or the reverse reaction dominate, the reaction is in equilibrium and there's no net changes in the amounts of reactants or products. So this is reaching equilibrium. There's no net changes in the amounts of reactants or products. Most often in biological reactions, the forward reaction dominates. The reaction moves from right to left. Sorry, left to right. But most of these reactions are irreversible. Once in this thing, once glucose and oxygen react to form carbon dioxide and water, it doesn't get reversed as easily. It doesn't get reversed as easily, if at all, unless you put a lot of energy into it, which is what plants do. So most of these reactions that are where the forward reaction dominates release energy. This is what we call exergonic. If you think we haven't talked about it in here, but you might have talked about it in lab. Exocytosis. Did you talk about cells in lab?
I don't think yet. We
Not
just
yet,
did
not-
microscopes last week.
Okay. Well, it's coming. You're going to be talking about exocytosis. It might be today. Exo, think of that as to exit something. Cytosis means cell. Bear with me just for a second here. I'm going to put some words up here. Write these down because we're going to see them a lot. Bear with me. I didn't mean to do that. So exo means to exit. Endo means to enter. Let me add this to it. Oh, I didn't mean to make it smaller. See here. I'm going to try something. Bear with me. Oh, that didn't work. Okay. All right. Bear with me. I'm going to erase this because I can't fix it. So exo means to exit. Exiting. Endo means to enter or entering. Cytosis, which we'll talk about in a week or so, means to a cell. So exocytosis means to exit the cell. Endocytosis means to enter the cell. Anytime you see the word cytosis, it has to do with something with regards to the cell. In this case, exocytosis exiting the cell, endocytosis entering the cell. Gonic, and I don't know where gonic comes from. Cyto I know means cell. I don't know where gonic comes from, but gonic means energy. I know I'm not a fast typer, so I'm gonna flip back now because I know you probably got that written down before I even finished typing it. An exergonic reaction is a reaction that releases energy. So the energy is exiting the reaction. So most forward reactions are exergonic reactions that thereby release energy. They will not go in the opposite direction. This is ATP hydrolysis. Oh, I'm sorry, bear with me. This is the production of ATP. And this is a really bad example. I'm going to change this because that isn't right. The breakdown of this is.
Where are you? Because we just still see your whiteboard.
Oh, shoot. Oh, shoot. Here, give me a second. Oh, darn it. I'm so sorry.
That's okay.
I appreciate you saying something.
I just was like, what the heck?
This is what we're actually looking at, guys.
There we go.
Okay. Chemical reactions that release energy going in one direction will not go in the opposite direction. So reactions that easily release energy won't go in in the forward reaction don't reverse themselves and go in the backward reaction very easily. Leo, no, you cannot be right there. Sorry, disciplining my cat. So reactions that release energy are not reversible. Anabolic reactions, which is the building up of things. So anabolic meaning to build up things, build smaller things into bigger things. Require energy. Oh, this is another word we need to add to our list. Of words. And I'll remember to flip this time with my screen. Endergonic means entering. Or another word for that would be require. Actually, let's just say Leo, no, you cannot be right there. Requiring. But remember, go
Is
ahead.
ender and endo the same? Just a different.
It's, yeah, they're kind of the same. They're kind of the same. One of them is, they're both taking in things. So endocytosis is taking things into the cell. Endogonic means that energy has to enter the reaction for it to occur. So they are kind of the same thing, yes. But let's say this instead with regards to ender. It requires it. You have to add energy to it for this reaction to occur. I know you can't see my screen. You're still seeing the whiteboard, so give me a second. I'll remember to flip this time. So endergonic reactions, anabolic reactions, so the building of smaller things into bigger things. So a series of chemical reactions that synthesize larger compounds from smaller compounds. Requires energy. It's an endergonic reaction. Catabolism or catabolism, depending on who taught you how to say it. You say it catabolism, depending on how you say it, whoever taught you, you'll learn it differently. So my mother's correcting my pronunciation. She's the nurse practitioner, so maybe we should listen to her this time. Exergonic reactions. So catabolism or catabolism or catabolism.
I keep hearing you say cannibalism, and I was like, wait, what?
Well, that's kind of close here. Remember that, mother, wait. That's the way you're going to remember this. Okay. Cannibalism is when we break down other humans. Cannibalism is breaking down larger things into smaller things. That's the way I remembered it for a long time. Was I thought of cannibalism. Kind of a grody way to think about it, but it works. You won't forget it. Catabolism are exergonic reactions, meaning they release energy. Most often, oh, she really, Mary? Here. Most often, this energy is released in the form of ATP. And it's invested in the form, you can't be right there. It's invested in the form of ATP.
What's ATP?
Energy.
Okay, it's just
I think we talked about it in the first chapter. It's adenosine triphosphate.
Okay.
And it's the energy form that your body uses almost always. And next time when we meet, we'll talk more about that, I think. But it's the energy form that your body uses most always. So catabolic reactions and anabolic reactions work in concordance with one another. Catabolic reactions, when larger molecules are broken down into smaller molecules, energy is released because we break bonds. Large molecules store energy in their bonds. Remember that potential energy source. When they're broken, when the bonds are broken, smaller molecules are produced. The energy is released in the form of ATP. And we can use this ATP that's released from this reaction to take smaller molecules and build them into larger molecules via the anabolic reactions. So we can couple these two. We couple reactions that release energy with reactions that require energy. Couple different, oh, really, Mary? I'm sorry, my mouse pad is really touchy. And this is a new computer, so I'm still learning more and more about it sometimes. So different types of chemical reactions. The first type that we'll talk about, synthesis reactions or combination reactions. involve the bond formation between smaller molecules or atoms. These are our anabolic reactions. If you remember, we talked about what did we talk about? Bear with me here. Remember, we talked about monomers coming together to form a polymer. When we were talking about hydrolysis and dehydration reactions with water. This is the reaction of connecting monomers together to make polymers, is one example of this type of reaction. The monomers of proteins are amino acids that can be bound together into a polymer that's a protein, which we'll talk about next week. Decomposition reactions are when molecules are broken down into smaller molecules or atoms. This is our basis catabolic reactions. We also, we have reactions that break things down, our catabolic reactions. We have reactions that build things up. Our synthesis or our anabolic reactions. We also have exchange reactions. Reactions that involve the breaking down and the synthesis of new bonds. So this is where parts of the reactant molecules, here's one reactant, here's another reactant. Parts of the reactant molecules exchange themselves. C binds to A and B, but B is by itself. A, B, and CD bind to form AD and CB. In this case down here, the phosphate, adenosine triphosphate, if you remember, tri meaning three, so there's three phosphate groups. The phosphate group gets bound to glucose, one of the phosphate groups. Another type of reaction, and this is very similar when we're looking at this one, think about ionizing things. Do you remember what it means when we form ions? Someone tell me what's the reaction required when we form ions? What happens?
The addition of electrons.
Yep. So you can either add electrons from an atom. You can add electrons to an atom, or you can lose electrons from an atom. So this is very similar. Molecules, rather than just atoms at this point, molecules can lose electrons. And frequently in biological reactions, hydrogens follow. So they can lose hydrogens. So molecules lose electrons, or molecules gain electrons with hydrogens. Molecules that lose electrons are said to be oxidized. molecules that gain electrons are said to be reduced. And if you remember when we were talking about sodium and chloride, sodium gives up its electrons to chloride. And then they form an ionic bond because of their opposite charges. Redox reactions or oxidation reduction reactions occur similarly in that the reactant that gives up the electrons always has another reactant that gains those electrons. And the products are the resulting materials that either gained or lost electrons. So magnesium loses electrons and takes on a positive charge. When it loses those electrons, it actually gives them up to copper, which loses its charge. You remember that 2 positive, because 2 positive meaning that there's 2 more protons more than there's electrons once magnesium gives up those electrons. Copper is working the same way. So before, it's an ion that has 2 more protons than it does the number of electrons. It gains those electrons and gets a neutral charge, a 0 charge. So these are reactions that lose or gain electrons. And there's just another way that we can refer to this is oxidation oxidation reduction reactions, or oxidation reduction reactions, or redox reactions are an exchange of electrons between the 2 reactants. And if you look at this one, the major difference here is most biological reactions. This is metals, are when you see the change in charge. In most biological reactions, you see a loss or gain of hydrogen ions by a similar pattern. You lose hydrogens, it becomes oxidized. You gain hydrogens, it becomes reduced. How are you going to remember this? That oxidation is to lose or gain hydrogens, and reduction is to gain, because it's the reverse of what you would think it would be. When I think reduction, that's always to lose, but that's not the case here. So the mnemonic that works for this, and there's a couple that work, but Leo goes Ger. What that means is lose electrons, oxidation, gain electrons, reduction.
Lose electrons.
Yeah, can you repeat that, please?
Do you see it typed here?
Yeah.
Yes.
Okay, so lose electron, and I'm going to put in here, I'm going to add something, or hydrogens. It can be electrons or hydrogens. Leo goes Ger. lose electrons, oxidation, gain electrons or hydrogens is a reduction. And there's one more. Give me a one. Oh, now it won't let me do it. So Leo, lose electrons and or hydrogens is oxidation. A gain is a reduction. So a gain of electrons or hydrogens is a reduction. Leo goes Gur. Another one, and this one I'm not as familiar with, lab rats. How does that one work? Bear with me here. Lab rats. All right, I'm not going to use that one because I can't remember how it works. I like the Leo goes Gur. Someone explained it to me at one point, and obviously I don't see it there. Yeah, I don't see it, so I'm not going to try to go do that one. Remember, the Leo goes Gur. So lose electrons is an or hydrogens is an oxidation. Gain electrons or hydrogens is a reduction. If before next time I remember what that lab rat one is, I'll tell you. First, are there any questions? I think in my head, this is a little easier than the first part of this chapter, which we just finished. I hope it is for you too. So remember that reactions that release energy and reactions that require energy can be coupled together.
We still see your white screen.
Oh, shoot. Thank you.
Mhm.
So reactions that, do you see it now?
Yep.
Okay. Reactions that release energy can be coupled to reactions that require energy. Also, all chemical bonds store energy, so they always store potential energy. A chemical bond represents potential energy. All chemical reactions involve either the absorption or the release of energy. Reactions that release energy are exergonic. Reactions that absorb or invest or require energy are endergonic. So the breakdown of ATP, remember that's our universal body fuel. ATP, breakdown of ATP releases energy that can then be used for other things. The building up of ATP requires energy to be absorbed, which is an endergonic reaction. All right, stay with me for 5 more minutes here. So we can couple these reactions. Energy released from an exergonic reaction can be used to drive or run an endergonic reaction. Go back. Sorry, bear with me just for a second. So endergonic reaction let me, bear with me just for a sec. Endergonic reaction. ATP is broken down. The energy from that breakdown is used to convert reactant 1 into product 1. I'm sorry, bear with me. I'm not explaining this picture very well. Give me one moment here. I don't like this. I don't like this figure. I think it's confusing. And I'm sorry, I thought it worked for me, and now I'm realizing how little it works.
You find it confusing, I'm sure.
Yeah, well, I'm like all over the place over here, but.
Right, so what I want you to remember, is I can break a chemical bond in one reaction.
Okay.
And when I break a chemical bond in one reaction, it releases energy because chemical bonds are a potential form of energy. It releases energy. I can use that energy to do other things that require that energy. So I can couple an exergonic reaction. Remember, that's one that releases energy. I can couple that to a reaction that requires energy. So I couple these reactions together, one that gives up energy and one that requires it. That's what coupling of reactions means. Is one reaction gives it up, the other reaction requires it. Yeah, I'll have to look at that diagram a little bit more, replace it. So summary of chemical reactions. You have oxidation reduction reactions. You have decomposition, meaning that's a breakdown. You get catabolism, that's also the breakdown. Synthesis, the building up. And anabolic reactions are the synthesis, the building up. Oxidation reactions, if you look here, oxidation, remember that's the Leo part. Oxidation is an exergonic reaction. A reduction is an endergonic reaction. So exergonic reactions, all reactions that release energy are oxidation reactions, decomposition reactions, and catabolism. All reactions that require energy are reduction reactions, synthesis reactions, and anabolic reactions. We can couple anabolic to catabolic reactions. There was a diagram earlier about that. We can couple oxidation reduction reactions. So the energy from one reaction is required in another reaction and used to drive another reaction. Are there any questions? I'm sorry, we have 1 minute. Are there any questions? Think about this. Spend some time with it over the next week. We will finish this chapter next week. And then I'll figure out what I'm gonna do with chapter 3. But it's an easier, I think it's an easier chapter to comprehend than this ever is.
Good.
That's what I was gonna say. I hope
It's
so.
still- But this is a basic chapter because a lot of what we're going to do is going to build on this.
Okay.
This is important for you to understand the future chapters. Work really hard with this. Because if you can understand this, you can understand the majority of what we're going to talk about for the rest of the semester. So spend a lot of time with chapter 2. And
Do we get
have-
4 chances with the quiz then?
You get 2 chances. No, you only get 2 chances.
Please double.
No, you get 2 chances. And the reason is because I want you to study before you take it. I don't want you to be looking up all the answers. I will, so you'll see that the deadlines for like chapter 2 quizzes like next week. We won't finish it, so I'm going to extend it out another week.
Thank you.
Yes, thank you.
Have a wonderful weekend, okay?
Bye.
You
Be
as well,
careful.
thanks.
I have a quick question.
Go ahead.
So I did my chapter 2,
Who am I talking to?
London, sorry.
Okay, no, it just doesn't show your name or anything, so I'm just making sure.
Okay. Sorry, not chapter 2, chapter 1.
Okay. Bear
I'm just
with
trying to
me.
figure out what the name of it was. I'm sorry.
Bear with me just for a second here, because I'm going to stop recording.
Okay.